All right, so we're going to look at the energy stored in an inductor, and similarly to what I did for the energy stored in a capacitor, I'm going to go ahead and derive this equation here, which basically tells us that the energy stored in an inductor is equal to 1/2 multiplied by the inductance multiplied by the current flowing through the inductor squared. Okay, and that is basically the same form of the capacitor equation, which was 1/2 C times V squared. And so you can see that they're similar, and the derivation is going to be very similar too. So I'm just going to go through that real quick, just so you can see where this equation comes from. It comes from, again, the integration over all time, basically integrate from time 0 to infinity of the voltage across the inductor multiplied by the current through the inductor with respect to time. Okay, and right off the bat, we know from our let's just use our charging equation or our energizing equation, because we want to energize the coil to figure out just how much energy is going to be stored in the coil once it's energized. We know that the current is going to be the final current times 1 minus e to the minus t over tau, right? I'm just going to keep it in terms of tau for now. Keep it simple. Actually, you know what? I'll just write the L over R in there. Why not? Just so we know what we're dealing with. And then I know that VL of t is going to be L times DIL dt. And if this is my IL, then all I have to do to get DIL dt is take the derivative of this thing with respect to time. And so let me do that real quick. That's going to just be equal to L times ILF multiplied by, and then I'm going to have a 0, obviously, for this constant term, minus, and then I'm going to have a negative 1 over L over R, e to the minus t over L over R. All right, that's my expression for the derivative. I can add these together because those two negatives make a plus, and so what I actually end up with is that EL, the energy stored in the inductor, is the integral from 0 to infinity of ILF times 1 minus e to the minus t over L over R, multiplied by this derivative that I just found, which is the voltage. This is the voltage. This was the current right here. The voltage is L times ILF times 1 over L over R, e to the minus t over L over R. All right. And so what I can do is I can pull the constants out of this term. I've got a constant term here, 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 and here. So I can say EL is equal to ILF squared. There's two of them, multiplied by L, and then multiplied by R over L. So my L's cancel. And then what I'm left with is the integral from 0 to infinity of just 1 minus e to the minus t over L over R, multiplied by e to the minus t over L over R dt. Okay? And so from this point, I'm just going to start writing L over R as tau. All right? And so I can say that EL is equal to ILF squared times R multiplied by the integral from 0 to infinity of 1 minus e to the minus t over tau times e to the minus t over tau dt. Probably don't need these square brackets, actually. They're kind of making it a little cluttered. You can just write it like this. And then let me go ahead and just distribute here, or kind of expand this out to where I have 0 to infinity, e to the minus t over tau minus e to the minus 2t over tau dt. All right, and so this is what I'm left with. I need to go ahead and take the integral here and then plug in my bounds, and I should be able to determine the energy stored in an inductor. And so let me go ahead and do that. It's going to be ILF squared times R multiplied by, in the first case, negative tau times e to the minus t over tau. And then for the second term, it's going to be negative tau over 2 times e to the minus 2t over tau. And then that whole thing gets evaluated from 0 to infinity. All right. And since I have two negatives here, I can turn that into a plus, and I'll just rearrange the terms. I can go ahead and write it as t over 2 e to the minus 2t over tau minus tau e to the minus t over tau, evaluated from 0 to infinity. And now all I have to do is plug in my bounds, so I'll go ahead and do that. Get ILF squared times r. Actually, I can factor out a tau as well from both terms, and then I get that this is 1/2 e to the minus 2t over tau minus e to the minus t over tau, 0 to infinity. Now I'll plug in the bounds, and my bounds are 1/2 times, so e to the minus 2 times infinity minus e to the minus infinity. Both of these terms are easily going to go to 0. Minus, and then I have 1/2 e to the negative 2 times 0, which this whole thing goes to 1, minus e to the minus 0, that goes to 1. And so what I'm left with is basically negative 1/2 minus 1, or just a positive 1/2 from this entire thing in the bracket. So I can say this is ILF squared times R times tau times 1/2. Tau, of course, is L over R. And so if I plug that in, I get ILF squared times R times L over R. The R's cancel, times 1/2. And what am I left with? I'm left with EL is equal to 1/2 times L times ILF squared, which is exactly what I expect to get. All right, and so that's the derivation for the energy stored in an inductor. We can see that it's equal to 1/2 multiplied by the inductance of the inductor multiplied by the square of the current flowing through the inductor. And in the next video, let's go ahead and solve a quick example where we utilize this equation to determine the energy stored in an inductor.